Today we will discuss the chapter 4, which is heat and temperature. We will review the concepts of the kinetic molecule theory, specifically the phase of matter, which is the temperature concept, and units of the temperature, which are the temperature scales. Also, we will discuss the heat concept and the specific heat concept. Just remember, these are the problems assigned for this chapter. This is the parallel group B of the chapter 4. We discussed last time that heat and temperature are not the same. In this case, we had two beakers in which we had water, but the temperature of the water is the same, 100 degrees Celsius. However, the amount of heat we had in each beaker is not the same. And the reason it's not the same is because we had twice amount of water in the right beaker. The beaker is on the right. We had 500 milliliters in this beaker, and we had 1000 milliliters in the other one. The temperature concept is related to the kinetic energy of the molecules. And for example, in this case, if we had ice, if we want to measure the temperature of this ice, probably we will have 0 degrees Celsius. And the reason is, in this case, the molecules in the solid state they can just vibrate, they cannot move. Yes, then the temperature is less. But if we increase the temperature, and what happens with the water, if we increase to 20 degrees Celsius or 30 degrees Celsius, the water is going to convert into liquid. Then the molecules now can vibrate, can rotate, and can translate a small distance compared with the size of these molecules. Then if we increase the temperature, the molecules can vibrate faster. Then when we are measuring the temperature, what we are really measuring is how fast or how slow the molecules can move. But if we increase the temperature even more, then the liquid can convert into steam, yes, or vapor. And what happens in this case, the molecules can move even more faster, they can rotate, they can translate, and they can also vibrate. But in this case, they can translate distance larger compared with the size of the molecules. Then if we measure the temperature, in this case, the temperature can be maybe 100 degrees Celsius. Then in this, probably we will have about 0 degrees Celsius. In the second case, we had maybe 30, 40, 20 degrees Celsius in the liquid state. But here we will measure about 100 degrees Celsius. Then this is why the temperature is related to how fast or how slow the molecules are moving. Then is related to the average kinetic energy of the molecules of the substance. Also, we mentioned last time, in the same way we can measure the velocity in meters per second, we can measure the distance in meters, centimeters, then we had units to measure the temperature. These units are the thermometer scales, and we had 3 different units in which we can measure the temperature. Is Fahrenheit. Fahrenheit is the most unit used in USA and in England, and there is 2 important points in these scales: is the freezing point of the water and the boiling point of the water. In Fahrenheit scale, the freezing point of the water is 32 Fahrenheit and the boiling point of the water is 212 Fahrenheit. In degrees, in the scale of degrees Celsius, which is less known for us, but is used in science and is also used in the rest of the world is this scale is degrees Celsius. Then 2 points that are important and I want you to remember is the reference point, which are again the freezing point of the water, which is 0 degrees Celsius in the Celsius scale, and boiling point of the water, which is 100 degrees Celsius. The other scale is used mainly in science, is the Kelvin scale. As you can see, in Kelvin scale, we don't have negative temperatures, and the reason is in science sometimes if you have negative numbers, it can be a problem for calculations, and this is why this is mainly used in science, and there is no negative temperatures. Again, the reference points are the freezing point of the water, which is 272 Kelvin, and the boiling point of the water, which is 373 Kelvin. As you can see, the division between these two reference points in the Celsius scale and Kelvin scale is 100 divisions. However, in the Fahrenheit scale, we have more than 100 divisions. And this is why we will see some fractions if we want to convert Fahrenheit into Celsius or Celsius into Fahrenheit. But if we want to convert Kelvin into Celsius and vice versa, we don't have fractions in the equation. Another important temperature is the absolute zero temperature, which is the 0 Kelvin, and this is the temperature in which the kinetic energy is zero, means nothing is moving. All the molecules are freezing. The molecules are not vibrating. Then, as we mentioned last time, we had some equations we can use to convert one equation into other, and because we say there is no 100 division between the reference point, between freezing and boiling point of the water, between Celsius and Fahrenheit, this is why we had here fractions in the equations, but if we want to convert Celsius into Kelvin, we don't have fractions. We have just 100 divisions in both scales. Then let's practice converting some temperatures from one scale to another scale. In this case, we have the average human body temperature, which is 98.6 Fahrenheit, and we want to convert this one into Celsius. Then what we can do is we will use this equation to convert, and just we will plug in the Fahrenheit temperature into the equation to get this one in. Let's write this one again. I don't know what happened. Then, I know. Yeah, sorry. Then we want to convert this one into Celsius. Then let's write the equation is 5. Then we want just plugging in this value. 0.6 Fahrenheit is 0.6 Fahrenheit minus 32. And now let's try to first, what we will solve first, what we had inside the parentheses, then is 66.6. Then we multiply by 5 first, and if we multiply by 6, we will get 333 divided by 9. And finally, we had equals to 0.0. Then we can say the 98 the 98.6 Fahrenheit equals to 37.0 degrees Celsius. And let's now try to convert 20 degree which is room temperature. We want to convert into Fahrenheit scale. We don't know how much this one is in Fahrenheit. And because we know the temperature in Celsius, just we will plug in that value. Multiply by 20 plus 32. Multiply, first we will solve, we multiply 9 by 20. First we solve the multiplication and then the addition. And we had 9 times 20 is 180 divided by 5 plus 32. Then the temperature in Fahrenheit, now we divide these two numbers, which is 36 plus 32, and finally we add this together. And this is Fahrenheit. And we had the 20 degrees Celsius equals to 68 Fahrenheit. And finally, we want to convert 300 Kelvin. Yes, we want to convert 300 Kelvin into Celsius, and we want to convert 300 Kelvin into Fahrenheit. Then we want into Celsius, and the equation we have is this one. To convert, because we want to convert into Celsius, first we will solve for this, for the temperature in Celsius, and we subtract this on both sides of the equation. Then we have the O then this equals to 300 minus 273, and this equals to 27. And if we want to be carefully with the significant digits, we will have 27.0 Kelvin. Degrees Celsius, sorry, degrees Celsius. Now we want to convert into Fahrenheit, then we will use the second equation, and will be this one. This is 27 plus 32. And in this case, we need to multiply 27 times 9 will be 243 divided by 5. First multiply, then we add. And first division will be 48.6 plus 32, and finally we had 80.6 Fahrenheit. answers are the two answers. Then 300 Kelvin equal to 27 degrees Celsius, and 300 Kelvin equals to 80.6 Fahrenheit. Now let's talking about the heat. Then when something is moving, we say that object has kinetic energy, and is high respect to some reference point. We say that object has potential energy. That energy is the energy we can see. As we can see the object is moving, we can see the object has some high respect to some point or some reference point. Then that energy we can see is called the external energy. Also, the objects have some internal energy, and the internal energy is the kinetic energy and the potential energy, which is associated with the molecules of the object. Then the kinetic energy is related to the vibrations, to the translation, to the rotation of the molecules. And the potential energy is mainly the potential. In this case, is the potential chemical energy. Is the energy between the molecules. Is the energy which bonds the molecules. Then the energy, the kinetic and potential energy of the molecules is called the internal energy. That energy is the energy, we cannot see that energy. As is the energy is in the object, but we cannot see that energy. For example, if we push a table, as which is in this example, if we push a table, if we exert some force against friction, yes, if we push a table, then what happens is that the work we are doing is converted into the kinetic energy. It is converted into external energy because we can see the table is moving. But also at the same time, this part of this work is converted into the internal energy because of the friction, the legs of the table become warmer. Then that is also warm the molecules increase the energy of the molecules of the table. And again, in the same way, we had some units to measure the temperature, which are, for example, Kelvin, Fahrenheit, or Celsius. We had also some units to measure the heat. Then in the metric units, we had one unit, which is calorie. And please pay special attention to, you see the symbol is a small c. It's a small c. What is the calorie? Is how much energy is needed to raise the temperature, to increase the temperature of 1 gram of water, 1 gram of water in 1 degree Celsius. Is how much energy we need to increase in 1 degree Celsius. We increase the temperature in 1 degree Celsius for 1 gram of water. Another unit is used to measure heat is the kilocalorie, and this unit is mainly used for food. It's in the package of the food. The calories is not this calorie, is this calorie. What is the difference between these two calories? And we need to be careful with this unit. You see here we have kilocalorie, and the symbol for kilocalorie is capital C. You see it's capital C, and the abbreviation is called, but we use big C. In this case, the abbreviation is small c. Then 1 calorie with big C is equal to 1,000 calories with the small c. Okay? Then they are not the same, and we have to be careful, don't confuse. Even if the letters are the same, but if this is a small c, then is how much temperature we need to increase in 1 gram of water in 1 degree Celsius. But if we had the big C, is how much energy we need to increase 1 kilogram of water in 1 degree Celsius. Then the amount of energy is different. This is why they are not the same. But they are related, as 1 calorie for the food, the big C, equals to 1,000 calories with a small c. Then when you are solving problems, you have to pay attention if the c corresponds, if the c is a small c or big C. If this is a small c, is this unit, but if there is big C, then is 1 calorie with big C correspond to 1,000 calories with a small c. Okay, then they are not the same. Again, in the problems, you have to pay attention if you have this abbreviation or you have this abbreviation. Then this 1 calorie with big C equal to 1,000 calories with a small c and equals to 1 kilocalorie. Another unit for heat is in the English system is BTU, or British Thermal Unit. Is the energy is needed to raise the temperature of 1 pound of water in 1 degree Fahrenheit. We're not going to use this unit, but I just want you know there is also this unit. Also, James Joule, also he found the mechanical equivalence between the calories and joules, and we will use this conversion factor if we need to convert calories into joules. Then 1 calorie equals to 4.184 joules, but 1 kilocalories equal to 4,184 joules. Now we want here to if we had a car with 1,000 kilograms mass, because it's kilograms, and it's moving at 90 kilograms per hour, means 25 meters per second, how many kilocalories are generated when the car brakes to stop? Then let's try to find the information. Let's try to write the information we had about this problem. This car has mass equal to 1,000 kilograms. The velocity, and probably we will use in the 25.0 meters per second. Then how many kilocalories? Then we know kilocalories means are the units for heat, but we know heat is another way of energy. Then we want to find, yes, the heat means the energy is, we want to find the energy, the heat generated, but we want this in kilocalories. Let me write this one again. Kilocalories. Then we want to know is how much the energy when the car is moving is converted into heat. Then if the car has this mass, is moving at this energy, means the car has kinetic energy. If the car is stopped, this kinetic energy is converted into heat. Then what we have to find is really the kinetic energy of the car. Then the kinetic energy of the car will be equals, then the kinetic energy equals to mass, but the mass is 1,000 kilograms. If you want, you can put parentheses here, and the velocity is 25.0 meters per second, and we had to square. And the kinetic energy, then 1000 divided by 2, we can try to reduce that, is try to simplify. This one will be 500.0 kilograms, and we solve this one. This power is 25 to the second power is 600 times 625 meters squared per second squared. Then the kinetic energy equals to let me check. Okay, then it's equal to it's 312,500 joules. But this is the energy that was converted into heat in joules, but we want to give this in kilocalories. And for that we will use the conversion we discussed in the last slide, which is 1 kilocalorie, because we want the answer in kilocalories. Then we will have 1 kilocalorie equals to 4,184 joules. Because it's kilocalories, is 4,000. And let's use this conversion factor to convert this into kilocalories. Then 4,184 joules times 1 kilocalorie. And we cancel out the joules. Let me write here the kinetic energy. Okay. Let's put some line here. Then we multiply by 1 and divide by 4,000, and we will get this. This is 74.7 kilocalories. Then the kinetic energy that is converted into heat is 74.7 kilocalories. Right. Let's review again. Then what is the concept of temperature? Temperature is based on the average molecular kinetic energy of the molecules or atoms that makes up the substance or the object. But heat is based on the total internal energy of the molecules. It's how fast is the energy related to the molecules, to the motion of the molecules, as to the translation, vibration, rotation of the molecules. Is the energy of those molecules, is the internal energy, which is heat. And here we had 2 cups with water at the same temperature, is 90 degrees Celsius, but here we had different amount of water. Yes, we had here 4,000 more water. Yes, here we had 250 milliliters. Here we had 1,000 milliliters, which is 1 liter. Is 1,000 milliliters. And here we have 4 times the amount of water. And this is why we had 4 times the amount of heat. Yes. However, the temperature is the same. Then this is, if we want to cool down this water, we need here 4 times the ice to cool this water. Yes. Then if the process in which we increase the internal energy, yes, and we increase how if we give more energy to the molecules, they can move faster, then that process is called the heating. The process in which we decrease the internal energy of the molecules is called cooling. Now we want to find the equation that correlates heat and temperature. Then first, let's analyze what variables are influence or are important when we want to heat some. When we want to heat some object. In this particular case, we want to bring this liquid or this water to boiling. What are the variables are important or can influence this process? Then the first thing is if we increase the temperature, we will have more heat. Yes, if we increase more the temperature, we will have more heat. The change in temperature means the changes between the final and initial temperature is direct proportional to the heat. More change in temperature, more heat. The mass of the substance. Yes. If we want to bring this one to boiling, if we have more water, we will need more heat. Yes, more mass, more water means more mass, more heat. Then mass and heat direct proportional. Another important thing is what kind of material we have. As we have mass or we have any other kind of substance, then if we have different substance, we will need different amount of heat. Yes, to bring this one to boiling, for example. Then let's review again. Then the heat is direct proportional to the change in temperature. More change in temperature, more heat. Yes, if the delta T is larger, the heat is larger. More mass, more heat. Yes, are direct proportional. If we put these two equations together, yes, if we put this equation together, then we have something like that. Yes, the heat is direct proportional to the mass times the change in temperature. Now, if we want to write this proportionality as equation, then we need to add a constant of proportionality. Then the constant of proportionality we add in this case is this C. Usually we use K, but this is just the name of the constant of proportionality, is the small c. And this is called the specific heat. Then what is the definition of the specific heat? Is how much heat, how much energy we need to increase the temperature of 1 gram of the substance in 1 degree Celsius. Again, what is the specific heat? Is how much heat or energy we need to increase the temperature of 1 gram of that substance. That substance can be any substance, water, gold, aluminum, any substance. We want to know how much heat we need to increase the temperature of 1 gram of that substance in 1 degree Celsius. In our textbook, we have the list for the specific heat for different materials. But before to go with that, let's see, we want to know what are the units for the specific heat. To know the units for the specific heat, what we want to know first is to solve for C. In that case, then we have heat equals to mass of the substance, specific heat of the substance for change in temperature. If we want to solve for C, we need to solve for, if we want to solve for the specific heat, we need to divide on both sides by the mass and the delta T. When finally we had the delta T equal to C. Let's write this one like that. And now let's write just the units. Then the units, yes, equal The units for heat is calories, can be calories. For mass can be grams, yes. And for delta T is degrees Celsius. Then the units for calories, let me do it like that. The units for the specific heat equals to calories per gram per degree Celsius. I want to show something. Then these are units less. I want to show, let's see if I can. I want to show also, we have this, then this is one of the units, yes, for a specific heat. Then we have this. If we multiply by 1000 and we divide by 1000, we are not changing anything because 1000 divided by 1000 equals to 1. Then these two are the same. These two are the same quantities. And if we had 1000 calories, we had this equal 1000 calories equal to kilocalories. 1000 grams is 1 kilograms. Yes. This is kilograms, this is kilocalories. Then what we can come to, this is another unit for, let me write here, this is another unit for, see, but one thing is you can see these two are the same. Then let me write, we have to be careful with this. We have to be careful with this because should be a small c. Okay. These two are the same unit. Okay. If we had 1 gram per degree Celsius, is the same if we had 1 kilocalories over kilograms per degree Celsius. And this is why here we have the same units. Yes, is the same value in this unit or in this unit. We have the same. And here we have the specific heat for some substance, and this is the intrinsic property of the material. Yes, is we can identify that material if we know the specific heat of the material. For water is 1, yes, is the reference value, and we had here for steam is for water, steam of the water is 0.48, and here we have the specific heat for some metals which are small values, and we will see why in case of metals the specific heat is small. In this slide, why we want to show is we want to understand what is the concept of a specific heat. Then in this we have 3 different materials. We had the same mass, as is 10 grams of aluminum, 10 grams of copper, we had 10 grams of gold. And we want to increase the temperature of these metals the same. We want to increase from 20 degrees Celsius to 100 degrees Celsius. For 20 degrees Celsius to 100 degrees Celsius, and the same case for gold. Means the delta T in this case, in all the cases, the delta T is 80 degrees Celsius. The mass in all the cases is 10 grams. This is the same mass in all the cases, we have 10 grams. However, the heat we need in each case is different. It's not the same. Yes, it's different. We need different. For example, in case of aluminum, we need 176 calories. In case of copper, we need 74.4 calories, but in case of gold, we need 24 to increase the temperature of the same mass for the same mass and the same to increase the temperature to 100 degrees Celsius for the same mass of the material, of that material. And why, if we have the same mass, we have the same delta T, why we need different amount of heat? Then the answer is because the specific heat of the specific heat of each material is different. For example, in case of aluminum is 0.22, in case of copper is 0.093 calories per gram per degree Celsius, and for gold is just 0.03. Then the reason we need just 24 in case of the gold is because we need just 0.03 calories to increase for increase 1 gram of water in 1 degree Celsius. We need less heat to increase 1 gram in 1 degree Celsius. But in case of aluminum, we need more heat. Yes, we need 0.22 calories to increase 1 gram of 1 gram of aluminum in 1 degree Celsius. We need more heat. And this is why in case of the aluminum, we need more heat, 176, and in case of the gold, we just need 24. Because the amount of heat needed to increase the temperature depend also the specific heat of the material. Then let's do some problem to try to practice the equation that correlate heat and temperature. And we want to know how much heat must be supplied through a 500 grams pan to raise its temperature from 20 degrees Celsius to 100 degrees Celsius. And what we know is the mass of the pan equals to 500 grams, and the initial temperature equals to 20.0 Fahrenheit, and degrees Celsius, and final temperature is 100.0 degrees Celsius. But we want to calculate how much heat means. We want to know the Q value, how much heat, if the pan is made of iron, and we want to also calculate what happens if the pan is made of aluminum. With this information, when they give the what kind of material the pan is made, what kind of material made the pan, then they are giving the information about the specific heat. Then we know if it's iron, the specific heat for iron is 0.11. Then for iron equal to 0.11. And in case of we need for aluminum, let's see, for aluminum is 0.22, is here, 0.22. Let's use aluminum just like that. It's 0.22. Okay. We don't need this. And let's calculate what happened, how much heat we need if the pan is made of iron. Then mass delta T. Mass is 500 grams. Iron 0.11 calories. Delta T is here. Let's calculate the delta T equals to 100 minus 20, and the delta T equals to 80 degrees. Then delta T equal to 80. Then we had 500 times 0.11 times. Then let's see, because it's heat, we expected the answer in calories. Let's see, we cancel out this one, and the final units is calories. And let's multiply this one together. 500 times 0.11 times 80 degrees Celsius will be equal to 4,400 calories if it's made of iron. Now what happens if it's aluminum? Then we do 500 times 0.8 times 8. If we multiply this together, again we cancel out the units, yes, and calories is the units we expected, is 8,800 calories. Because the mass and the delta T is the same, we expected some answer like that. You see, the amount of heat we need is the double, yes, it's twice the amount of heat we need if the pan is made of aluminum. And the reason is, you see, the specific heat of the aluminum is twice the specific heat of the iron. And this happens because the other variables are the same. Mass is the same in both cases, mass is the same, and temperature, delta T, is the same. Just the specific heat is changed, is twice. And this is, we expected twice amount of heat. There is two ways we can transfer energy. There is two ways we can increase. Let's first discuss in what ways we can increase the temperature of some substance or some object. Then we can increase the temperature if we can increase the temperature if there is some difference in the temperature of the two objects. Yes. Then this is similar to the experiment we did in class. Remember, we had cold water, we had hot water, and we just we used the aluminum bar to connect these two, to connect the cold and the hot water. And what happened is, after some time, the heat was transferred and they reached at the same temperature. The heat was transferred from the hot water to cold water. And in this case, you see, we had a similar idea. We had cold water, and we had in another cup we had hot water. We put one into another, and after some temperature, they reached to the thermal equilibrium, and they had the same temperature. Yes. Then always the energy is moving from the region of high temperature to the region of lower temperature. And this is always, the energy is moving from high to lower temperature. The other way is the object can gain energy from any other form of energy. Yes, for example, mechanical energy, radiant energy. Yes, if outside is sunny and you put some water in some cup, and we put this one outside, and you go after 1 hour, you will see the water is warm, because this water gain radiant energy. Then there is two ways, is if there is some difference in the temperature, or if there is that object, that substance gain energy from any other form of energy. There is basically there is three ways the heat can transfer, or the heat can flow. Yes. Can be by conduction, by convection, or radiation. The conduction is just for direct contact. Yes. And if the object is in direct contact, then we have conduction. But convection is for the motion of masses of molecules. And in this case, the molecules has to move to transfer the heat. And radiation is the energy can travel in the empty space. Yes, this is the only energy can travel in the empty space is the electromagnetic radiation. And let's discuss these three, and this is the last thing we will discuss in this section. Let's discuss these three ways to transfer heat, or three ways in which the heat can flow. By conductions, we say is transferred by direct contact. Let's see what happened in this case. If we hit the end of this tube, what is happening is the heat is going to transfer in this direction, molecule by molecule, as in this direction. Because it's transfer molecules by molecules, but because they need to be in contact, then what happens is these molecules, when start heating, is going to transfer the energy, is going to start vibrating faster, 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 faster. Yes, it's going to, by direct contact, yes, it's going to transfer the heat. And this is why if we measure the temperature in different points of the tube, we will see the temperature is not the same, because it takes time to transfer to get the homogeneous temperature to all the tube. Yes, probably after some time you will get the same temperature when the heat is transferred to all the molecules. Then in the conduction mechanism, the energy is transferred from molecule to molecule by direct contact. How fast the heat is transferred depends on the temperature difference, the area, how big is the object, the thickness of the object, and also depend on what kind of material, because we know the specific heat also is important when we define the heat. And again, the conduction is when the energy is transferred by direct contact. The materials can be classified according to how good are they to conduct the heat. Then if they transfer the energy efficiently, they call conductors, and usually good conductors are metals. Yes, are good conductors. The insulators, they are not good conductors of heat. They transfer the energy of the heat inefficiently. The best insulators, usually they have the space between the molecules are larger. Then this is one of the characteristics of the insulator. The distance between molecules are larger compared with the distance between molecules of the conductor. The best insulator is the vacuum, because there is no molecules can pass the energy. And here we have some the list of some conductors and insulators, and we can see the best conductors are the metals, and the good insulators are, for example, vacuum and air, and also the glass, the wood. Yes. In this, the space between molecules are larger. Another way we can conduct the heat is by flow, by convection. In the convection is this this transfer of heat occurs only in liquids and gases, because it's the only state of matter in which the molecules can flow. In case of the solids, remember, in solids the molecules just can vibrate, they cannot move, and this is why they cannot flow, and then they cannot transfer heat by convection. Only liquids and gases can transfer heat by convection, because the molecules can move. In this particular case, we say the energy is transferred by the motion of molecules, and in this case, what happens is when the air passes through the heater, the air is warm, and this air pushes the cold air again push the cold air to the heater. When this pass is warm and is push again the cold air to the heater, and in this cycle is keeping up to all the air or all the room become warm. And the same thing happens, this is in case of gases or the air, and this is the case of liquids, as here is that water is close of this surface become warm, this is moving up, yes, and this push the cold water, this water become warm, and this starts circulating, and this happens until this temperature start boiling. The last way we can transfer heat or the heat can flow is by radiation, and we say this happens when the energy is transferred in the empty space by electromagnetic radiation. Yes, by the electromagnetic radiation. Then what are the kind of energy can flow into the empty space? Are all this kind of energy of the electromagnetic spectrum. The electromagnetic spectrum or electromagnetic radiation. The only energy we can see is the visible part of the electromagnetic radiation. Yes. The other radiations we cannot see, but we know they are, and we use it for many applications, and this radiation include gamma radiation, X radiation, infrared, microwave, and this is in microwave or radio signals include all these signals we have here at the end. Then again, what are the radiation? The heat transferred by radiation is just this correspond to electromagnetic radiation, because it's the only radiation, the only energy can move into the empty space. Another important thing is any object, any substance at the temperature above the 0 Kelvin, or which is called the absolute zero, always emits some radiation. Then just to summarize, we discussed today what is the concept of the temperature and its units. Temperature is based on the vibration, or is based on the kinetic energy of the molecules of the substance. Heat is the internal energy of the substance. Yes, this is the heat, and the units for temperature can be degrees Celsius, can be Kelvin, can be Fahrenheit. In case of the heat, we had calories, but because heat is an energy, can be also joules. The equation that correlates heat and temperature is these equations, and in this equation also we had the mass of the substance and the specific heat. We say the specific heat is the small c, and the units for the specific heat can be calories, but also can be kilocalories, kilograms degrees Celsius. And there is 3 different ways we can transfer the heat, or the heat can flow. Can be by conduction, direct contact. By convection is the flow of the molecules. The radiation is the energy can travel in the empty space. And this is all for today.